This is the second lecture in our mini lecture series on descriptive statistics. In the first lecture of the series, I introduced descriptive statistics and discussed the measures of central tendency, the mode, median, and mean. In this lecture, we are going to focus on the measures of variability. In the upcoming and final lecture in this series, we will address the normal distribution and confidence interval. At the end of this lecture, students should be able to define and differentiate between the measures of variability and be able to determine the most appropriate measure of variability to use based on the level of measurement of the variable data. As you should recall from the first lecture in this series, measures of central tendency allow us to determine the center of the data sets. While the mode looks at the most commonly occurring individual value or values within the data set, and the mean is heavily impacted by outliers, measures of central tendency do not provide us with information about the differences between and among the many individual values within a data set. Furthermore, it is highly improbable that the values in a data set will all be identical. There are individual differences and variations between people that make us unique, and that is why we need to collect descriptive data. In other words, some level of variation among the individual data values should be expected. Therefore, anytime we calculate measures of central tendency, we also need to calculate measures of variability, which tell us about the change between the individual data values. Calculating both measures of central tendency and measures of variability allow us to achieve a more thorough grasp of the data and better describe our data set. Simply stated, measures of variability tell us how much the data varies or changes. Measures of variability describe how spread or dispersed a set of data is. These measures indicate the degree to which individual data points differ from each other and from the center of the data. Furthermore, measures of variability provide information about how well a measure of central tendency actually represents the middle, center, average value in the data set. When the data values vary a small amount, the measure of central tendency will be most accurate. When the variability increases or the difference between the individual values increases, the accuracy of the measure of central tendency decreases. There are multiple ways of computing and presenting variability. In this lecture, we will focus on the four measures of variability that you will most likely see in scholarly work: the range, the interquartile range, variance and standard deviation, and finally, degrees of freedom. To help us understand how to apply measures of variance, we're going to be using the same data set we have been using throughout this course thus far. I have provided a copy of the data set here for your convenience. The range is just like what it sounds. It is the difference between the largest and smallest values in the data set. The range is very simple to calculate. You first need to sort your data set from smallest to largest numbers, and you can see in our example I have done that for years of nursing experience. You then identify the largest data value, which for our data set is 44, and subtract from that the smallest data value, which in our data set is 1, meaning that our range is 44 minus 1, or 43 years. The range can be calculated for ordinal level categorical variables as well as for continuous variables. While continuous variables are numerical, ordinal variables, even though they are categorical, provide an order or ranking to the categories. Furthermore, the range is best suited for normally distributed data sets where there are no unusual data values or outliers. The range is not useful for nominal level data because there is no ordering to nominal level data. So there is no way for us to say what the largest and smallest values are. The range is extremely simple to calculate, and that can be very appealing. However, we must be cautious about using the range as a measure of variability because the range only uses the highest and lowest values in the computation, which is what makes it extremely sensitive to outliers and unusual values. Sometimes the range gives us, especially if the data set is large and there's a huge difference between the range, that doesn't tell us a lot of information. Look back to part 1, and our range for number of years for nurses is 43 working years. Sometimes researchers want to report the range in a more understandable way, and they will report the range as the lowest and highest values. For example, what we would say in our data set is that the nurses' years of nursing experience ranged from 1 year to 44 years. And this gives us a better understanding with the extremely large range. The interquartile range is the difference between the 75th percentile and the 25th percentile. Percentile is a measure of location and tells us how many data values fall below a certain percentage of observations. Therefore, the 25th percentile is the data value that the bottom 25% fall below, and the 75th percentile is the data value that the bottom 75% fall below. When calculating the interquartile range, you need to have your data set listed from smallest to largest. And I have our data set for years of nursing experience already sorted for us. The first step in determining the interquartile range is to identify the median, which we discussed in a previous lecture, and we know that the median for our years of nursing experience is 7. The 25th percentile would be halfway between our smallest number and our median. And our 75th percentile would then be halfway between our median and our largest number. In this case, it turns out that we have an even number of data points when we go to determine the median between either the smallest number and our middle number, or between our middle number and the largest number. Therefore, we follow the pattern that we would use for determining a median with an even number of data points. So between 7 and 44, the middle is between the numbers 19 and 22. Therefore, add them together, divide by 2. Our 75th percentile is 20.5. We do the same thing with our 25th percentile. The middle between 1 and 7 is between 2 and 3. Add those together, divide by 2, we get 2.5. Our interquartile range then is the 75th percentile, which is 20.5, minus our 25th percentile, which is 2.5. And this gives us an interquartile range of 18. If you remember, our range from our smallest to our largest was 44 minus 1, which is 43. Our interquartile range, which is where the middle 50% of our data values fall, is 18. Or in other words, the middle 50% of our data values will fall between 2.5 and 20.5 years of experience. Like the range, the interquartile range is useful when working with continuous level variables. Because the interquartile range does not use the smallest or the largest values, it is less sensitive to unusual cases and extreme outliers, and therefore is better to use than the range if the data is not normally distributed or has unusual cases. Like the range, the interquartile range is not useful for nominal level data because there is no ordering. Because the interquartile range requires us to find the median and then to find the percentiles, it is also not useful for ordinal level data for the reasons that we discussed as to why the median is not useful for ordinal level data. While the interquartile range is an overall improvement from the general range, the interquartile range still has significant limitation in that it does not account for every data value within the data set. Variance and standard deviation are two measures of variability that use all of the data values in the data set. Therefore, these measures are more precise in capturing information about variability than either the range or the interquartile range. Variance is defined as the measure of how spread out the data points are. In other words, variance is used to determine how close individual data points are to the mean. Variance is calculated using the following equation. The sum of x minus x bar squared divided by n minus 1. In this equation, following the order of operations, we begin inside the parentheses with x minus x bar. X is the individual data point values, and x bar is the mean of the data set. We determine each individual x minus x bar and then square that. The symbol sigma means that once we have done every single x minus the mean and squared them, we are to add all of those equations together. Following that, we are going to divide by n minus 1, where n is the number of data points. I know this sounds very confusing, but we're going to walk through it with our data set. As you can see, I have our years of nursing experience data provided here. Notice I do not have the data in numerical order, and we do not need the data to be in numerical order. From our previous lecture, we know that the mean of this data set is 12.36. Therefore, to calculate our variance, we will begin starting from the left, going to the right with our data. Our first data point is 1. So therefore, we will take 1 minus 12.36, our mean, and we will square that. We will then add together every other data point. So you can see I have the second data point, which is also a 1 minus 12.36 squared, all the way up to, and that's what the dot 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 means, our second to last data point is 44. So 44 minus 12.36 squared plus our final data point, 2 minus 12.36 squared, dividing all of that by 25 minus 1, because 25 is the number of data points that we have. If you were to do this calculation, you would get a variance of 153.9. So, what does that mean? Well, a variance of exactly 1.0 would imply that all of the data points in our sample are the same. The higher the number for variance, the more spread out our data points are, the larger the range of our data points is. And we have a very large range of 44 minus 1, which is 43. In general, a lower variance is preferred to a higher variance. However, determining the meaning of variance, such as our 153.9, is fairly ambiguous. For that reason, you will rarely see variance reported in the literature. Instead, what is often reported is the standard deviation, which is the square root of the variance. And before we move on to talk about standard deviation on the next slide, I do want to clarify that you will not be expected to calculate a variance by hand. I show you the formula here so you can understand how the data was calculated, how the statistic was developed. Like the other equations we have discussed in this course, technology software such as Microsoft Excel or IBM SPSS is used by statisticians and researchers to calculate things such as the variance. The standard deviation, which is often abbreviated as SD, is the average number of points by which the individual values in a data set vary from the mean. The standard deviation is calculated by taking the square root of the variance. The standard deviation is the most commonly reported measure of variance in the data. And that is because we can gain a lot of information and insight from the standard deviation when we apply what is called the empirical rule. The empirical rule can be applied to normally distributed data or data that follows a normal bell curve. Based on the empirical rule, 68.3% of the individual data points will fall within one standard deviation of the mean. What does that mean? That means that if we take our mean and we add the standard deviation to it and subtract the standard deviation from it, 68.3% of the data values should fall in that range. 95.5% of the data values should fall within 2 standard deviations of the mean, and 99.7% of values are within 3 standard deviations of the mean. Generally speaking, data results are considered statistically significant if they are further than 2 standard deviations from the mean. And that's getting into inferential statistics, which we will discuss later on in the semester. But I just wanted to kind of get your minds thinking about the standard deviation and what the standard deviation is. So, looking at our data set for the number of years of nursing experience, we knew from the previous slide that our variance is 153.9. Our standard deviation is the square root of that, which is 12.4. We could apply the empirical rule here if we knew our data was normally distributed. However, I will let you know that our data set is not normally distributed, and I know that based on the calculations that I did. Another key giveaway here is that if you look at our standard deviation, it is larger than our mean. Our standard deviation is extremely large for a data set that has a range from 1 to 44. Therefore, we cannot apply the empirical rule accurately in this case. However, I wanted to show you the standard deviation for the data set we have been using, as well as introduce you to the empirical rule, which we will discuss further on throughout the rest of the statistical portions of this course. This slide is an oversimplification, and I hesitated to add this slide the way I have it. However, my OCD tendencies made me want to stick with the layout that I have been using for this lecture. So, with variance and standard deviation, you are most likely going to see the standard deviation in the literature because the standard deviation is in the same units that your data set is in. If you recall, the variance was a squared value. So when we take the square root, we are back to the same unit of measurement that we had. So the standard deviation allows us to get some insight about the spread of our data, comparing it specifically to our data mean. The variance is more ambiguous for basic statistical analysis than the standard deviation is. You will likely not do much with variance unless you were to go on to a PhD program or to do advanced statistical education. So what I really want you to take away from a discussion of variance and standard deviation is to have a basic foundational understanding of standard deviation being a spread from the mean average, and the empirical rule regarding standard deviation for normally distributed data sets. Degrees of freedom is the term used for the estimate of the range of variability. When working with a sample, the degrees of freedom is always equal to the size of the sample, which is denoted as n minus 1. Therefore, for our sample of nurses, since our sample contains 25 nurses, our degrees of freedom would be 25 minus 1, or 24. In other words, the degrees of freedom is the number of values in a calculation that are free to vary. A great way to think about this is to think about the 4 drink cup holders that you get at fast food restaurants. Consider that you and 3 friends order drinks. When the server goes to put the drinks in the drink holder, they can put the first drink in any of the 4 slots. The second drink, they have 3 choices as to which slot to put the drink in. The third drink, they have 2 choices. However, when they come to the 4th drink, there is no choice, there is no variance in where that drink will go. Thus, you have freedom as to the order or the placement up until the very last person in your sample. Unlike the other measures of variance that we have discussed thus far, you will want to calculate the degrees of freedom for every sample. This is because the degrees of freedom are going to help guide the statistical tests that you will use to analyze your data. Degrees of freedom are directly related to the sample size. If you remember, they are the sample size minus 1. In quantitative research, a larger sample is usually preferable to a smaller sample. Thus, it would logically follow that larger degrees of freedom are preferred to smaller degrees of freedom. If the degrees of freedom are too small, which is referred to as insufficient, then you run the risk that your statistical results will be unreliable and not accurately capture the true underlying relationships. As a summary and recap, there are 4 measures of variability that you need to consider when working with a data set. As we discussed in our last lecture, measures of central tendency give us information about the center of the data set. Measures of variability provide us with more robust information about our data set and how the individual variables relate to each other. The first measure we discussed was the range. The range can be calculated for variables at the ordinal level of measurement or continuous variables. We cannot calculate a range for nominal level variables because a range is based on ordering. A range will either be displayed as a single number that equals the largest value in the data set minus the smallest value, or for ordinal data, and sometimes even for continuous data, the range will be listed as a spread from this to this. Remember to place the data in order before calculating a range. The interquartile range is similar to the range, but can be used only for continuous level variables. The interquartile range looks at the range of the middle 50% of the values, which is why we cannot use it for ordinal level data, because we cannot guarantee that we would not have to split the average between 2 values to get the 25th quartile or the 75th quartile. Similarly to the range, we need to order the data to calculate the interquartile range. The benefit of the interquartile range over the range is that it is not impacted by outliers. We then discussed variance and standard deviation, which can be calculated for variables at the continuous level of measurement. Variance and standard deviation tell us information about the data points. Variance looks at how spread out the data points are in general, and the standard deviation looks at, on average, how far the data points vary or move away from the mean. Variance is a good calculation for mathematicians and statisticians. For you as nurses who are using statistics in a very applied sense to understand, calculate, and analyze your data, you are going to want to focus on the standard deviation. Standard deviation is a very important concept to understand because as we move forward in this course, we're going to talk about standard deviation and how that relates to statistical significance of your results. Finally, the degrees of freedom can be calculated for variables at either the categorical or continuous levels of measurement because the degrees of freedom are looking at the size of your sample. The degrees of freedom are telling us the range of variability within our sample, and the degrees of freedom for a sample is always equal to the sample size minus 1. Degrees of freedom are very important to helping us determine appropriate statistical tests and therefore should be calculated for all samples.